Right, good evening, everyone. Right, we are still looking at our loci, we are still looking at games with uniform. Want to look at a scenario where the follower is placed at an angle. So we are going to look as to how we can come up with the displacement graph and also the projection displacement graph, where you are supposed to divide the angular divisions into subdivisions as well. Loci, right? That's the locus of a point. In particular, we are looking at games. Type of followers, we have got the wedge-shaped follower, which again can be referred to as a needle-shaped or a point. We also have got the roller follower, right? Which can also be referred to as a needle, which can also be referred to as a. Right, we did that in our first sessions, and we also have looked at the roller follower in terms of construction and application. So this lesson is basically a recap of what we have been doing so far. What is the advantage of the roller follower over a knife-edged follower? Remember, a knife-edged is the same as a shaped or a point or a wedge-shaped follower. Right, advantages of a roller follower over knife-edged follower is that the roller follower has less wear and than knife-edged follower. Power required for driving the cam is less due to less frictional force between the follower. Then the function of the roller followers. The roller follower is used in a wide range of applications such as cam mechanisms of automachines, dedicated machines, as well as carrier systems, conveyors, bookbinding machines, tool changers of machining centers, pallet changers, automatic coating machines, sliding fork of automatic warehouses. Right, then we want to look at the construction of these cams where we are using roller followers. As always, I want you to pay attention to what we are doing, see everything that we are doing so that you'll be able to remember, and practice everything that we are doing so that you're able to understand and apply this on your own. That's enjoy the lesson and good. There you go. Right. The given task is as follows: the detail of the roller follower for a disc cam, as well as the center of the camshaft. Right. So these are the details that we would make use of, as well as the center of the camshaft. We are going to look at that. The specifications: the maximum distance from the camshaft center to the cam profile is 78. The roller follower is used. The rotation is anti-clockwise. So we have got this setup. We have this is our camshaft. Remember, the moment you draw a camshaft, you line, you hatch that. Then we are also going to make from here to there, which is the maximum diameter, which is 78. Let's look at the motion that the cam rotates at constant velocity, imparting the following uniform motion to the follower. From 0 to 75 degrees, the follower falls, right, through 35 millimeters. Right, so we have got from here to there, that's 78. Just hold on. 75 to 120 degrees. The follower is at rest. So the follower is neither rising nor falling. Okay. Right. Remember, in rest, it can also be referred to as it's dwelling, it's stationary. Right. 120 to 240 degrees, the follower rises 53 millimeters. Right, remember, we have got the distance from here to there, it's 78, that is the maximum. This follower can rise. Rising, it's moving away from the camshaft center, and falling, it's towards the camshaft center. That you need to bear in mind. So what it means is, right, at some point, the distance from here going downwards there, right, should be 53. So that when the fall rises to the maximum, it should rise a height of 53. Remember, we said that it would fall 35 millimeters initially, then else it does not rise. Then from there, it would rise back to the maximum, which is 78, okay? 240 to 285, the follower is at rest, right? Means it's stationary. Right? It is also falling, okay? Not rising, not falling, but when it is at rest. 285 to 360 degrees, the follower returns to its initial position. So this, right? Using a horizontal scale of 30 degrees is equal to 7 millimeters and a displacement scale of 1:1. Draw the displacement graph for the given motion. Label the displacement graph and include. Draw to scale 1:1 the given roller follower in its starting position. Right, so we need this to draw this in its starting position. Show the direction on the curve, hedge the shaft, and show the constructions. Right, let's start with shaft. Right, it says diameter 20, right, which means radius 10. So I'm going to measure 10. Open to 10 millimeters. Then draw this. Sorry. So, okay. So that is our cam. That is our cam shaft. The moment you have got that cam shaft, you hedge it. Right. So that's our first part. We put the camshaft in position. Right. We are not given the minimum distance. So the minimum distance means. So it means it has to be found by way of construction. So what we need to do, right? We need to locate the roller at its maximum position, right? Having this one at 30 degrees, which is center line. So I'm going to do this faintly first. Right, then measure from to this 8. Then can draw this. You can even draw a line like that. It would take you, that is displacement graph. Right, and the diameter of the roller is diameter 14. So radius 7. There you go. Right, and the from here, right, which is from here to there, that's 50. We also measure 50. Right, the size of the follower in terms of the shaft is not given. Let's make this 10. Right, I think that would suffice. Um, outline. Right, we can now define the line. Right, so that's the from the camshaft center all the way to the floor. There should also be a center line here. Like that. There you go. Right, so according to the motion that is, right, we are supposed to have the movement of the follower from 0 to 75 falling 35 millimeters, not necessarily from here, right? Because at some point the follower is to rise from the low point to the maximum point 53 millimeters. What I want you to do, right, you measure from here to there 53 millimeters. Let's measure 3. Right, so the 53 would define the maximum displacement. So I'm going to draw a faint line like, all right. So our displacement from here, that's a maximum of 53. Then at this point, we also again a circle radius for the roller, radius 7. This should be outline. So what it means is that the distance from here to there, therefore, will now give us a minimum diameter. Right, let's just measure and check what is our minimum diameter from here to there. Right, it's about 18 millimeters. Then we can draw faintly. This does not require to be outlined. Once we have got the camshaft diameter, we have got the minimum diameter, we can also now define the direction right in between the two. There you go. Right, so that's the direction. It's anti-clockwise, so it's moving in that. We are done with the setup in terms of what is there. Okay, all right. Then we need now to measure from this point going up, so that from the starting point we should be able to form 35 millimeters. So from here, let me measure 35. There you go. Yes. 10, 20, 30, and 35. Then we draw another line again. We draw another faint circle, radius 7. This is our starting position. It's like that. Right. So we start here, then for 35 millimeters. Then at some point we are going to come back, right, and rise from this point to that point 53 millimeters. Okay. Now, once we have done this, we can also now draw the maximum diameter, which is 78 as our radius. Like this. Let me just take this one so that you'll be able to see clearly. This one down. Right. So this is the maximum diameter. We can even divide this one into 12 equal parts. Let's do this. Right. Remember, for present's sake, do not go inside the space between the shaft and the minimum diameter. Not that you'll be marked wrong if you do that, but you want your work to be presentable. There you go. Right, we can label, but this is our point 0, which is also 360 degrees. Right, it's moving anti-clockwise, so we number in a clockwise direction. Right, so this is 30, right, 30, 60, 90, right, 120, 150, 180 degrees, 210, 240, and 270 degrees. That's 300, 330. But as you know, we have got other divisions in between 90 and 60. We need 75, right, which is 15 degrees. Right. Now that we have got this in position, the next thing that we want to find is the length of the displacement graph from here to there. Right. We are that 30 degrees is equal to 7 millimeters. Right. Therefore, 360 degrees is equal to, right, we can do cross multiplication here such that we get 360 degrees over 80 degrees multiplied by 7 millimeters, right, over 1, which would give us 360 divided by 30 multiplied by 7, right, we would get 84 millimeters. That is the length of the displacement graph. Let's see if we have sufficient space to measure 84. If I mark here, that is 84, like that. There you go. Right, we can make this one slightly darker than a construction line, not as dark as an outline. Just to make it clear. Okay. Right. Then we can divide this one into 12 equal parts. That's 1, 2. There you go. Take any straight edge and the set square. Right. Remember, you can measure 7, 7, 7, 7 to represent the 30 degrees. But because there is a mark which is awarded for showing this graphic, the division of the length of the displacement graph. So just make sure that you show this construction as well. Do the vertical projections. 7 millimeters, representing 30 degrees. There you go. Right. Right, like we said, right, when the shaft or the follower is moving towards the shaft, it's falling when it's moving, right, away from the shaft, it's rising, okay? Right, so irrespective of the position, you'll find that the follower in, right, going towards the shaft that is falling, moving away from the shaft that is rising, okay? Right, so we are going to say this is 0, right? Then we need to check how many degrees from 0 to 75. So what we require here, right? So with 30, we have got 60. We need to bisect this or find a way of dividing this one into 12 equal parts. Equal parts. Right, I can do this. Take a 45-degree set square supported by the 30-degree angle, right? You come here, draw a line like this. Also do the same. this. So this is a halfway, right? Then you draw a line through that. Go. What you indicate here, this point is 75 degrees. We have got 30, 30, and 60 plus 15, that's 75. Right, then from 75 to 120, the 90, 120, right? So we need to indicate 120 there. Right, then from 120 to 240, 120 to 240, so that's 150, that's 180, 210 to 240, which would be here. Right, 240 to 285, right, that's 270, we need 15, we do the same thing. Bring your 30, 60 degrees. This is in line with how the line has been drawn, but we need to miter to create an angle of 45 degrees. So this edge would act as if it's the T-square. Like this. Right, that's 270. We need something here. We take this one up. So that's the bisector. Then we draw a line through that. There you go. That's 285, okay? Right, 240, 270 plus 15, that's 285. Then 285 to 360, right? So we now have got 360 degrees, 0 degrees, and so forth. So now this is the movement in terms of the linear movement of the follower, right, from this point to that point, which has been stretched as a line, right? So from here to there, we said it's 84, divided this one into 12 equal parts. Then once you have done that, we know that in terms of our displacement graph, right, is starting at this point, which is here, not there, okay? All right, and it should form 35 millimeters through to how many degrees? To 75. So we need to connect from here to there, right? So it has fallen 35, but also covering 75 degrees, right? Then from 75 to 120, right? It's from 75 to 120, right? It's dwelling, right? It's resting. Then it rises from 120 to 240, from this point to that point. Like that. Right, initial position, falls towards the camshaft center, then it dwells for 15 degrees, then it rises 53 millimeters, which is the maximum displacement. Then 240 to 285, 240 to 285, it's here. Right, then 285 to 360, it returns to original position. The original position is this one, so from here to there, right, we need to connect. To 85. Right, 285, that's 300, 330, that's 360. We can outline this now. There you go. Right, so that is the nature of our displacement graph, right? Falls, dwells, rises all the way in terms of the maximum displacement, dwells, then comes back to the original position, which is that. Right, you can now label the displacement graph. Remember, in dimensioning, right, if you follow the principles of dimensioning, you read from left to right, from bottom to top. Okay. So here, that's the displacement. In millimeters, or displacement 1:1. Right there we write, that's our displacement graph, such that it's readable. That's our displacement graph. Here we write a rotation in degrees. Then we also specify the scale, right, which is 30 degrees is equal to 7 millimeters, like that. Right, so those are the labels that are required in terms of making sure that we are able to draw our diagram properly. Let me just position it properly. Right, there you go. Right, the next thing that we require now, right, is to project from, right, the line on the graph as well as the angular divisions in terms of the linear divisions from here. That's 0 to 30, 60, then 75. You take that now back to the line of action, right? Remember, this is where the follower will be able to move, and we refer to that one as the line of action, right? But before we do that, we also need to define, right, the 75 millimeters or the 75 degrees. So stand here, take and bisect this. Let's draw a line and up. Stand on the other end. Or you can do that by making use of a 45 and a 30 degrees set square. And take this one all the way. So there is 30, 60, and there is 75 degrees. Right, where else do we have something? 75 to 120, then, right, 240 to 285. Right, so this is 270, we need a division here. You can do the same thing or make use of a 45 and a 60 degree set square, which can also be a 30 degree set square. And indicates how this says to pass through to the other end for construction purposes. Right, so then you indicate that this is 285 degrees. Right. So you now have got all the systems in place, right? All what we need to do now is to project, right? To project from here to the line of action. Faintly. That's 60. And you stand at the camshaft. Describe an arc. That's the center. You do the same for 60. That's the center. Right. Then from 60, right, to 75 degrees, or from 75 degrees, which is this point, but we also require this up to 120. Do this 120, which is here. Then once you have done that, just to make sure that we won't get confused, you take the radius of the follower, come here, right? Then describe an arc. Right. You may draw a complete circle, but it's not necessary. You also come here, that's at 60. You describe another faint arc. Then at 75, right, like that. At 90, then up to 120. There you go. So these are the positions of the follower relative to the movement of the camshaft. All right. Now, if we were to just give it a try as to how this would look like, we would connect this one like this all the way. Remember, it's the underside. It's the underside. Where there's a dwell, you simply outline with a canvas. Right. Then we go. Right. 120. This is 150. So you project this 150. 180, and then we have got 210. Then we come back to 240. Right, let's start with this one. Right, normally when it has changed direction, like here, we need 150. Right, I'm going to do this there. Right. That's 180 there. That maybe direction-wise, it would close. Let me do this so that you'll be able to see, right? So that's 210. There's already 240. Take the radius again, like that. Come here. Just a semicircle, it will suffice, like that. That's 150. It's 180. That's 210. Then you come here. That's 240. Right, there's a dwell from 240 to 285, so we go to 270, right, just the underside, and 2 to 285, so like this. Then from there, we now have got 300, 330, then 360, which is our starting position. Right, we do the same projections. Right, this is for 330. This is for 300, right? So we have got 300, 330, then 360. We take this again, right? You open to here, and that's 330, right? You increase the size. This is 300, right? Take the same radius again in terms of the size of the roller. Take this one, go to the 300 mark, right? Describe a semicircle like that. Go to the 330 mark, right? You do the same, you describe the roller like that, right? When we have got a dwell from 75 to 120, we outline using a canvas. So I'm going to outline from here to there. Like that. Then there is also another dwell, right? This is 210, this is 240 through to 285. Stand here, right? And open to the underside of this, right? Just check to make sure that it's touching, like that. Outline this. So that's how we treat the dwell. We use a canvas. Right, so then from there, connect. But with the underside, just erase this. So we do the same this side. And there you go. Right? So we know, right, from 240 to 270 through to 285, that's a dwell. From 75 to 120, that's also a dwell. Right, once you have done that, then you can outline the cam profile itself or the cam disk. Remember, when you outline, you can now correct, right? And this has to touch. Right. Here, of course, it could have been on the outward a bit, but that is it. You now have got this is the description of the chem disk. The next thing that you want to do, is to label some convenient like that. That you label either you write chem disk or disk chem like that nicely, so that you direct the examiner exactly where he or she needs to check the information that you have provided. So there you go. We now have got our complete chem, which is as a result of the information that has been provided. Right, initially we were given the distance from here to there is our maximum diameter. Right, then we were told that the follower in its starting position has to fall 35 millimeters from somewhere. And we needed to find that somewhere by first establishing the overall displacement, right, which is the maximum displacement from here to there, right, which would give us 53. Right, once we have defined the 53 from here to there, then you can measure from the lowest point to the starting position, which is 35 millimeters away from the center of the follower, right? And the moment you have drawn this follower in position, you are able now to establish the minimum diameter by simply drawing a circle that would touch the underside of the follower. What is key with regards to the roller follower is that you make use of the center of the follower in terms of that roller, which is the circle. So you might also require just to draw here the center line to give it a bit of meaning. Right? You can also do the same here like that, so that we know for certain that we have got this. This is a follower which has moved from here, right, all the way to that point. And how many millimeters from here to there? It's 53. But the starting position has to be 35 millimeters from the lowest point, which is that. So that is key. You need to establish that position first, which is the position from here to there, which is 53. Then you measure 35, which is the starting position, which would also be the end position on the other side. So I hope you understood how we went about constructing this chem. Right, when we meet tomorrow, okay, right, for our interactive session, we are going to look at the application of other types of motions, which is the simple harmonic motion, as well as uniform acceleration and retardation, by making use of either the wedge-shaped follower or the roller follower. Boys and girls, I hope you enjoyed this lesson as much as I did, and I hope to see you again tomorrow, and good night.